Thank you. So I think I know everybody now. So any questions from last time? And if some question pops up in your head in the middle, you can always just ask them. I wanted to make sure everything is pretty much clear so far. Okay, so where were we at the end of last time? So we were talking about, in the part one, electrochemical dynamics in batteries. And it was an example for any general electrochemical system. But it's easier to explain things when you have something concrete to talk about. So I talked about how battery works, how different components, what are the different components batteries, and then how the partial differential equations govern them. And from there, we identified some key material properties. And started to talk about how they are measured and calculated and how, where we get them. So that's where we left off. And that's where I'm going to pick up today. But where we are going today is how microstructure affects electrochemical dynamics, and some highlights from simulations that actually demonstrate that electrochemical systems tend to amplify the stochasticity in microstructures, and talk more about that. And then hands-on session is going to include some phase field model application, diffuse interface model application. So I have to, develop it between now and then, but that's what's coming up. So, so these are the different parameters that we talked about. Open circuit voltage, which basically representative of the thermodynamics of the material. Thermodynamics of material, and then you can measure them by charging, discharging a battery with a reference electrode very slowly. Diffusivities can be measured by titration techniques. Both actually, I only had a PIT last time, but PIT and GET both works. And EIS, electrochemical impedance spectroscopy, exchange current density can be measured by potential sweep and getting the IV curve. And conductivity can be measured for individual components by looking at the IV curve, basically Ohm's law. So, so this is kind of schematic of what those things are. Potential sweep, I think people just change voltage and what current you get. EIS, electrochemical impedance spectroscopy, uses a alternating current. So you may put a sinusoidal perturbation to the applied potential, and you do the, and it could be a current as well. You can do one way or the other. Basically have like Ohm's law with kind of generalized for alternating current. So you have a kind of complex form of the resistance, and that includes this phase shift. That allows us to extract more information from the data. Titration techniques, they has kind of step change applied to potential current. So this is a for GET galvanostatic version of it. So you go from zero current and then step it up to one current. And then look at how the potential change, the measured potential changes. So you get this relaxation. So initially you have something like this, and you have instantaneous resistance. But then it changes. The system changes because you have ions that are moving around, and you have this kind of decay-like feature, and then the system relaxes. and then you stop the current, and then again you go back to the original state like this. And then because the system changes, you get the different value at the end. So all those dynamic techniques allows us to extract the kinetics of the system, not just the kind of static state or static properties. But sometimes we can also get these quantities from the lower scale, like atomistic or density functional theory calculations. So I wanted to give you a couple of examples of these. So things that can be potentially measured are some dynamics of the system or diffusion kinetics, such as diffusivity of mobility, then we also electrochemical kinetics, like reaction rate. So I'm going to talk about the first two first. So how do we do that? So you start with, this is just one example of how you go by to obtain this information. So you can start with density functional theory calculation. You calculate some selected energy landscape in the as you change the occupation number, which is represented by this sigma. With the lithium occupies certain spot that are allowed to occupy. And then you construct this Hamiltonian that is based on not the not the original hard to calculate one, but you basically kind of divide it up into some bases. So you break it up and then try to find a good description of what you would get if you did the calculation from the first principles, but based on the those coefficients, evaluate those coefficients, which are the interaction parameters, right? So like this is if the interaction between the occupation in two sites, and you have this coefficient. If they're not, they don't interact, and it's going to be 0. This is like a 3-body type interactions. So you can expand this until you have something that's accurate enough. Once you have this is much more efficient to evaluate computationally, right? This is just a function. So then now you can actually stick it into a statistical mechanical framework. So like in the Monte Carlo method, you can evaluate this exponential factor, right? That's going to tell you what's the likelihood of having that state with this energy. So you can actually evaluate the partition function, and then you can use that to evaluate the free energy of the function of the system as a function of the concentration of lithium. So like these occupation numbers are related to like to how much of the spots lithium sites are occupied. So you can actually calculate things like free energy of the system, or once you have a free energy of the system, you can calculate chemical potential, etc. You can you can do that with the grand canonical Monte Carlo method. We can also use kinetic Monte Carlo approach to evaluate the mobility of lithium in this system. So then we have this, chemical potential as a function of the concentration of lithium, or mobility as a function of concentration of lithium, and then you can stick that into like microscale simulations, like phase field model that goes into this evaluation with this mu or L, right? So that's one way to connect them. But there was another factor that was discussed in the equations, which is, you know, you have a transport in this material, transport here in electrolyte, and then at the interface, the reaction rate couples those equations. So that's electrochemistry, and then that's what, you know, Yog talked about, and it's really the focus of the IPAM. I do hope that we can also look at other areas as well, but I think the improvement in the bridging the length scale for reaction from ab initio to continuum is really, really important. Then it's something that's not well developed yet. So that I'm really looking forward to working with everyone on these. Now, often we just can't get all the parameters. So when all fails, we go for parameter optimization. So this is an example. This is the first thing that we did in this area, parameter optimization area. And it's actually not related to electrochemistry at all. So our colleague had this idea of developing an experimental apparatus that this is I'm sorry, I probably should have put the name, but Karina Chapman was a collaborator, but we wrote a paper that's in collaboration with her. So this is heating element holder that has a groove over which heating element can be wound. And then over here, there's more density of the heating element versus this way. So over this distance, so you put the sample that's like, you know, in tube. One side of the sample tube, you're going to have a different temperature compared to the other side. So the idea was, you know, it worked really well, is that you can do one single experiment, but sample different temperatures, right? So it's like a kind of high throughput way of characterizing temperature effect on the material. And then in particular, this was a synthesis problem. So start with whole bunch, so we have to identify all the parameters, right? And here there were 10 parameters. And so you have to decide, oops, we have to decide the range of each of the parameters. And so that's what's shown by this kind of like this first line. And then we did latent hypercube sampling so that we efficiently sample large parameter space. We ran the simulation, calculate the errors, difference between the measurement, the experimental measurement, and our simulation data. And then we calculate the kind of like a distribution of the error, and then find the lowest 10% error range. And then we, if it's usually not accurate enough, so there's still like a large range here, like the error is large. And then so what you do is you repeat this process over and over, but it's actually don't have to do it too many times. You have to do it only like, I don't know, here it's 15 was what we went for, and only because this one still has a bit of range there, right? So so it's actually quite, the parameter set converges quite quickly. And then at the end, we were able to get really good fit between the, between certain range that we really cared about, between the simulation result and the experimental data. And why is this important? Actually, I should say. Okay, so they already had that, but then once you have a simulation, you can actually use the simulation to redesign this configuration of the material.
So how many parameters do you have that you need to?
There are 10 here.
10.
Yeah. Yeah, so it's big, right? 10-dimensional space, and we're like, can we really do that, right? But it actually works pretty well, this approach. So, and it converges pretty well. And if we didn't care too much about this one, we could have stopped after, I don't know, even like here, right? So, and for electrochemical problem, so we try to narrow down as many parameters as possible from experiments and simulation input. But when we try to simulate the whole cell, we coarse grain. And I'll show you some of the equations later on. So those are like, transport properties that are also modified by the microstructure. So it's not like you can just measure it. So in those cases, we also have to kind of like, do some parameter optimization. So this is for cell. And so this is for anode, by the way. So this is for the normal electrode. So it's like pseudo one-dimensional. We did a parameterization and using this as a training set, using the particle swarm optimization method, and we get good agreement as shown here. And then we were able to show that actually that parameters were pretty good because we also had the validation data set where there are features. So the way what we wanted to do with this work was to make the anode to be anode to tolerate high rate. So in order to avoid plating, lithium plating, we had to make the lithium transport really fast, right? So the one thing we did that our collaborators did, Professor Neil Desgupta's group, was to make holes. And so we had the data from this type of anode. And then we used this data, but then just changed the geometry in the simulation. And we were able to match up. And then this was not because of training, this is really validation data, right? We started out with this to use, to obtain the parameter set, material parameter set for this electrode, and which includes the microstructure effect. And then just change the geometry. So, and we get a good match, yes.
Just a very quick clarification question. What's the difference between unstructured and structured? Is this the...
Yeah, unstructured is like, there's no, oops, there are no holes.
This is within the electrode.
Yeah, so this is a top view of the anode, graphite anode. So what you're seeing is the graphite. And the unstructured ones are the ones that just the normal, what they do is you put the, you put down the graphite and you do something called calendaring, which is pressing. And then, so it's like totally one-dimensional, right? Like kind of on the average. If you ignore the particles, then it's one-dimensional. No holes, right? And then, so that's the unstructured one. And then this simulation is just 1D simulation. And this one is a 3D simulation because you had to look at those holes here. The holes are actually filled with electrolyte. So it's a lithium transport path that you're putting into this anode.
So
does that make sense?
It means that if we change the microstructure of the electrode, so the parameter, the model, will needs to be changed.
Yes, you have to train it again. Although, if you know, and I mean, not microstructure of this hole, but the microstructure here, right? That's what you're talking about. Is that correct? When you say microstructure, there are two things here, two levels. This is hierarchical. There's a microstructure associated with this gray area, which has a particle, a whole bunch of particles. And then that is specific to the specific pressure they put in for calendaring, etc., right? So if you change that, yes, you have to train it again. But this is a very quick calculation. It's one dissimulation. Does that make sense?
So I'm just trying to understand. So this parameter means that we have to change the parameter of this PD, basically the PD model,
Yeah.
the phase field, all these kind of parameters.
Yeah. No
This
phase field here, but yeah.
If we change the microstructure of this.
If we change those holes, if you change the size of holes, for example, no, we don't have to. But if you change the source material for the graphite, because graphite particle size can be different depending on who you get it from, or even like the specific batch. So if you change that, then you have to do this again. Yeah. Yep.
So when you do this sort of retraining, if I understand you did retraining from unstructured to structured, what parameters?
There is not retraining right here. Retraining this, this is a training data. It matches because we trained it with.
We trained it.
Yeah. And then we just
run. You don't have to retrain it.
No, not in this case, because this material over here is the same between the two. The only thing that was changed was geometry.
Okay. Then I guess my question is a little bit higher level then. Are there generally parameters in the model to which the performance is most sensitive?
Oh, yeah. And then we actually used
with a particular type of physics.
Yeah, we actually studied that, and then we use machine learning to kind of figure out what is more important. I mean, obviously you can just tweak it and see, but yeah, so that's a separate talk, but yes.
Okay, but I would imagine the Butler-Volmer sort of coefficients and things like that.
Yeah. So open circuit voltage is one of them. That's quite important. And then actually diffusivity. And then, again, it depends on the system, how you made it. But the diffusivity, for at least in the anode, because these are actually like because of the calendaring process, you have a kind of platelets-like shape. So the lithium diffusion has to happen like in a very tortuous manner. So diffusivity of electrolyte is quite important. Okay. So quick review. The material properties are needed for electrochemical dynamics modeling, and parameterization can be done in many ways, including experimental numbers, but also from using lower scale modeling. And then when there's usually 3 uncertain parameters, and then you have to use some ML to get that done. So any questions up to this point? Yes?
So you said on the last slide that you used particle swarm optimizers. Did you find that you needed to specially tune the hyperparameters of that to work?
I think this, because we had a lot of, we didn't have any convergence issue. And then we also we had enough of like, so this, okay, so this is maybe it's a nice kind of aside, but so this is at different rate. This is the voltage as a capacity of the battery cell at different rate. So 0.1 C, which means 10 hour, C over 10, right? 10 hours. This is charging, and you can see, basically what you see here is pretty much very close to the open circuit voltage of the graphite. So this idea, we usually ideally use slower than 10, but this was what we had. 30 is better. And then so this is mostly thermodynamics, parameterizing thermodynamics. And then this change going from here to here is due to kinetics, right? You're trying to drive the system faster and faster. You're trying to charge it faster and faster. And then there's inefficiency, and then you have to, overcome the concentration polarization, and so you get, you have to, put more voltage towards the charging. So so there's a systematic way that you can actually get this right. So you can constrain the thermodynamics with the lower rate. And then you're left with some kinetics parameters, which makes it a bit easier to converge because there are fewer parameters by that time. Does that answer your question? Okay, great. Any other questions? Okay. So then, so next I'm going to talk about microstructure effect, and I'm going to introduce a material called lithium iron phosphate, LFP, and it is another one of those lithium intercalation compounds. Just to review, right? This was the key in rechargeable battery, enabling rechargeable batteries. You can get the lithium in and out of these materials without destroying the crystal structure. But they knew, you can make this material with lithium, with lithium or without lithium. It's nice because it's earth abundant. So a lot of battery materials have like cobalt, rare earth, right? But this is iron. You can find them. And then but what people thought in the like 70s when they were looking at different materials, they thought this was really, really terrible material for rechargeable batteries, because first of all, electrical conductivity is really low. That means how do you get the electrons there, right? And then and it's also two-phase material. Usually, like two-phase means that you have to create an interface. So you're going to get some hysteresis out of that. You lose energy by creating interface. So, but then they found out after making it into teeny, tiny, particles, by nanosizing it, and then coating with, okay, so nanosizing by itself didn't actually work out. It was something that was tried, and then, but then it was coated with carbon, and then it started to work. So nanosizing basically made it more difficult to introduce interface within the particle. You're going to see some intraparticle phase separation in the simulation later on. And then this coating with carbon introduced a way of carrying electrons to enable the reaction. So there are other complications with this material, though, very anisotropic. Anisotropic mobility, anisotropic interface energy. Mechanical properties are also anisotropic, and electron conduction is anisotropic. So it's very interesting. It's just really, 1D simulation isn't good enough in this material. There was a lot of calculation work that was done by Gerseira's group on this material. And indeed, when you look at the free energy of the lithium iron phosphate, you see this kind of like a barrier between lithium-rich, lithium-rich, and the lithium-poor area. Okay, and so when you calculate the equilibrium potential, you see something that looks like this, where you have an inversion in the chemical potential as a function of lithium concentration. So, so this has a huge consequence in how lithiation occurs in this system, And also, you will see that this actually amplifies the stochasticity in the microstructure. So in particular, I'm going to kind of focus on particle size distribution. So there's a particle size distribution. You may have small particle here, large particle there, etc. And then that actually, this inversion makes it really like more prominent how that plays a role. So here is a simulation setup. This is just two particles, one particle, one small particle, one larger particle. There's a lot of note with like DOD, which is depth of discharge, but it is equal to lithium side fraction of a particle. Or if it says cell DOD, it is like overall lithium side fraction. And because this is cell DOD, all of them, the simulations are galvanostatic condition. So cell DOD is proportional to the time. So it's same, this is same as time axis. And it is exactly how much lithium there is in the cell. And so you get a straight line going from 0 to 100%. And simulation looks like this. Okay, the small one gets lithiated first, and then this is just repeating. Okay, so that's the end. Small one lithiates first, and then that larger one lithiates later, which overall makes sense. You have reaction rate per unit area, right? And so, and then it's as long as all the local potential is about the same, you're going to have the same rate all over. And then for given equilibrium potential. So initially, the concentration is the same. It basically starts at 0. So initially, the reaction rate is the same on both larger particle and then smaller particle, larger particle and smaller particle per unit area. But there is more volume in the larger particle, so the smaller particle, which has less volume, is going to fill up faster because the capacity is lower. And then that's when things happen, right? Like, so this one starts going up higher, and then all of a sudden, actually, we may not be able to see in the movie, but all of a sudden it accelerates in terms of how quickly the lithium fraction changes in the small particle. So this is for the small particle. While the larger particle, surprisingly, at least at that time, it actually dilithiates. Larger particle actually dilithiate, which might be hard to see over there. And then it can only lithiate after the smaller one is done lithiating. And if you look at the potential, it does, this funny thing, right? Like this. So, and then this, we asked, is this also there's a voltage fluctuation and non-monotonic concentration evolution that are observed in the two particle simulations. And so, we asked, is this something that's very unique to two particle simulation? So we started to look at the larger system. And we introduced the size variation, log normal size distribution, and then they're randomly placed, but at small enough volume that there shouldn't be too much of a potential difference in the electrolyte. And the simulation looked like this. I'll let you watch it for a little bit. What do you see? Anybody? It is looping, but then it goes back to the beginning. Okay, so the beginning now.
Look at the smallest ones.
Smallest ones.
Yeah. Smallest one lithiates first. Do you see something else?
Do we have different sizes in the small particles? Because it looks from my perspective this way. But, I mean, like
You see groups? Is that what you're saying?
yeah,
Or
well, I see one that looks a bit bigger than the other one, but I don't know whether it's the perspective view.
so this is log normal. I mean, small number statistics, but log normal 65 particles. So it is continuous distribution as much as 65 particles can do. So do you see kind of like a wave? 1, 2, 3, 4. Oh, I think there are 4. Anyway, so and then you can actually visualize this. So here, what is plotted? The color is the lithiation level, right? Like so, this is red means pretty much 100%. So small particle lithiate first, like like you found out, and then, but you see this kind of like band, this band, this band, right? So there's 1, 2, 3, 4 waves, okay? So and if you look at the small particle, one of the small particles, it does this. I'm sorry, small particle, it does this, I'm sorry. Small particle, large particle, which is this one, does this. So it starts lithiating, both of them. Small particles, take off. Large particle delithiate, and then start lithiating again. But then another wave happens. And then at that time, it delithiates again. And then finally, its own turn comes, and then it can lithiate. And while the large particle are doing this, small particle also kind of like lithiate and delithiate, just a small degree, but does that also. So why does this happen? And then there are some important things that could, impact, like, if you are like, it's like it could cause fatigues, right, in those particles because they are like elastic material. They are like expanding and shrinking in this during this process. So what is happening? So first, I have to kind of tell you a little bit about how to read this diagram, right? So this is the voltage as a function of particle DOD, so the lithium concentration. And the equilibrium potential looks like this, right? And if the applied potential is over here, it looks like it's like opposite. Applied potential over here, this difference, if the concentration is here, this difference is the driving force for lithiation. And that's because voltage is defined for electrons, and this is positive, right? Lithium is a plus. So this is flipped. So just remember that if you look at this means this applied potential is the difference between, okay, so if the applied potential is over here, for this particle, it's not going to do anything. If it's over here, it's going to delithiate. And then it's over here, it's going to lithiate. Make sense? It's just that the orientation, chemical potential and voltage is just flipped. Just the signs opposite. And then the direction, positive direction is different.
Sorry, what is the single particle equilibrium potential? So how I can imagine this? This is if I kept the particles separately?
Single particle, yeah, it's just it's just for the material. I guess you could say just for the material. So it's for lithium iron phosphate. If the applied potential is here, then it's not going to do anything. It's in equilibrium. So if the applied potential is anywhere else, then it's going to do something, either lithiate or delithiate. If the applied potential is down here,
in order to get this single particle. to do first the calculation to first get the form of the single particle?
Yeah, this came from the ab initio calculation. So it's this one. It's this one. Yeah. So it came from that free energy. So okay. So just want to make sure, like sign looks opposite, right? Usually you say, like down the hill, so there should be negative sign. But here it's like opposite. So now we can try to understand what's happening. So you have 4 particles here. So 1 and 2 have more lithium. So it's actually sitting over here on that diagram, right? Sitting over here, 1 and 2. And 3 and 4 are less lithiated, so less in particle lithiation level, so the particle depth of discharge. And so they are sitting over here. And if the applied potential is over here to deliver the current, then only ones that are going to lithiate are 1 and 2. And actually, in fact, 3 and 4 will de-lithiate. It's going to lose lithium from itself. So this is going to go this way. This is going to go this way. Okay, so this is the picture over here. 1 and 2 went to the right side now, right? Let's see. It would be nice if I can manage using this, but now it's so that 1 and 2 move to the right on this figure, and then 3 and 4 kind of slipped back on the other side. And then it's going to keep going until the 1 and 2 hits this point where applied potential is equal to its equilibrium potential, and then 3 and 4 go to the other side and then has the equilibrium potential. So, and then at this point, now if you still have to drive the current, right? So the applied potential is going to actually shift in order to obtain the current out of those number 3 and 4 particles. So the applied potential is going to shift, right, in order to deliver the constant current. So now that gives us understanding of what's happening here. And when the smaller particles undergo rapid lithiation, they actually extract the lithium from other particles, as you can see in that diagram. And then when the larger particle actually on the other side phase transform, they extract lithium from the smaller ones, and then you can see these bands, faint bands in blue. Faint bands in red, as you see over here. That is what you see over here. Faint bands in the blue region is actually these dips. So, and then we asked, what about the spatial difference, positional difference? So now we just forget about the size difference. Same size across just a long domain that's like reasonable thickness, and then see what happens, right? So sometimes it's nice to have the answer before you have to try to explain it. Okay, so this is another setup, same particle size, and then this is the simulation. So initially you get kind of like overall increase in the concentration, and all of a sudden, once closer to the electrolyte that has or separator has a bit of an advantage, small advantage, and then they transform. And then in the process, actually, it extracts lithium from other particles that are slightly, lithiated ahead, and then change the salt concentration, lithium plus concentration in the electrolyte. So this is really complex, right? This is just all the same size particle. And you see this kind of like very much like, almost like an avalanche, like, stick and slip type behavior. So, and then here, we are not even looking at size distribution. So, and so you have to, in order to actually model this system properly, you have to include both the size distribution as well as the positional distribution. So electrochemical simulation is really like multi-scale thing, right? Like I talked about how the atomic level or electronic structure calculations can inform the particle level simulation, but also what we really want to know is what happens to the battery, right? Eventually, at least like a cell scale, or maybe not the like actual battery, but then the like at least the ones that are in a lab scale cell. So we need to somehow, just like this atomic scale calculations can inform, we have to come up with how this particle level simulation can inform larger scale simulations. So the approach we've been taken is to develop tools to accurately predict the behavior using direct simulation. So those are the ones I just showed you. And you can develop understanding using the simulation results, right? Like what I was explaining, why those kind of like, interparticle phase separation happens. And you can also include things like anisotropy in the system. And then we have to come up with mean field description that are, accurate, capture some of the things that we find out over here. And I hope to give you a little bit of an example of that. And then eventually to apply it to electrode and cell performance simulations. So one of the ways to coarse grain the particle level model is something called porous electrode theory. So, so you can, assume the particle to be like a spherical. So you just have like a differential equation for spherical coordinate, which gets coupled with other equations that are in the kind of like a bulk of the electrode. And then you have a transport in electrolyte, so effective transport property that includes the tortuosity effect, porosity of the electrode. The current continuity also need to include the fact that the entire material in the electrode are electrically conducting. So you have this effective conductivity and also effective conductivity of the solid, and then you have electrochemical reaction equation, and then so you have all these coupled equations, but kind of like coarse-grained or averaged out over the over the cell level, and then just like some kind of representative volume of the microstructure. So one of the things we did was, can we capture this behavior that I just showed you in the porous electrode theory simulation? And by property parameterizing it, yes, it actually does a pretty good job, right? So porous electrode theory result. So this is potential as a function of lithium occupation, basically. And the red curve is the direct simulation that I showed you. And so you have this right? And then blue curve is porous electrode theory. So you have blue curve, and then it's not doing too bad, right? So, so that kind of gives us confidence as to like we can coarse grain the particle level with proper handling of complications that happens within, for the thermodynamics of the system, anisotropy of the transport, etc. But here, particle size distribution is not included. So this means that you have to also do that separately on top of this. So you have to actually modify this equation. So you are going to have like some kind of distribution in the particle size for that equation. So okay, so that's kind of like the story of the LFP work that we've done. It's very, introduction to LFP, highly anisotropic, tendency for phase separation that actually amplifies the, the stochasticity in the system, particle size difference. You have some large particles, sometimes you have smaller particles, and then that actually amplified in the signature of the potential as you charge and discharge. So that's caused by this interparticle phase separation, and it can happen due to size distribution. It can also happen due to spatial position, the difference in spatial position, because you have the different electrostatic potential at the different region, different depth of the cell, right? Like the cell is like kind of like a layer, and then depending on how close you are to the current collector or how close you are to the electrolyte, you are going to have different electrostatic potential. So, yeah, question.
Can you go back to the slides where you had this kind of hierarchical structure?
Yep.
So not quite sure. Yeah, this one.
Yep.
So you have on the lowest level the atomistic electronic structure,
Yep.
and then you go to the next level of the particle. So does the particle then represent like a single grain, or is it like a?
This is single grain. This is a single grain.
Okay, and
Yeah.
then your next one, where you have the different beads, is basically the representation that you have grains that may be of different size. And that are some, okay.
Yeah, that's right. That's right. And then over here is actually this is a porous electrode theory calculation where it actually has like 10 bins in particle size distribution. And this is actually the cell. It's not real cell. Well, it's a cell that our experimenters are using. It's a small coin cell, but it's not like this kind of cell, right?
Yeah, not sure. It was just for me to try to put it into a picture.
I'm just curious, when you see this sort of wave phenomena, I guess it's at level 3.
Yep.
This complex electrode, where you see the robbing, the small rob the big of their lithium. Is that parasitic? Is that a parasitic effect? Is that
not parasitic.
Is that something you would like to eliminate, or is that something you can take advantage
so
of?
actually, if the particle is large enough, then you'd have phase separation in the particle, which means you're creating interface, and that is probably bad, right? I mean, that was one of the reasons this material system wasn't considered. By nanosizing, you reduce that. You reduce the it makes it harder to create interface, and then also introduce the large pre-existing interface, which is the surface of a particle. So that allows us to kind of eliminate the hysteresis from that. And because the interface is already there, it's phase separating, but it's not costing too much energy.
So when you say
say
phase separating, do you mean inside a single particle?
So there's an intraparticle and interparticle phase separation. So this is would that play here? Yeah. So it's phase separating between group of particles. Yeah. So. Yeah. And then if parasitic is just generically mean you mean like it's not desired. it probably is not a great thing to have because you saw this kind of like a fluctuation. So you are spending energy doing this, right? So it is ideally
You just target something.
removed. Yeah.
When you want to be, yeah. You want to be. So ideally, you want them all to be the same size. That would be.
Yeah, but that's hard to do.
Yeah, okay.
Engineering, we just grind them up.
That's someone else's problem. The goal of engineering is to take your problem and make it someone else's problem.
Yeah. A question there.
And you also made the assumption that these particles were spherical.
Yeah. So these are spherical, just to make it simple enough. But we actually, I don't have time to talk about it, but we had a more complex model where it was kind of different shapes and also allowed, that depending on the size, allowed phase separation to occur within the particle also.
Okay. Is it known at least that the particles are always convex, or can they have sort of straight?
Because they're pretty small. We wanted to kind of see what the thermodynamics does in that system. Would the behavior change is probably a key question. So if it's large enough and you let the phase separation to occur, then the behavior will change. Because the equilibrium potential is going to be different, right? So the thing about the other case, assuming that phase separation is suppressed in the particle because the particle is small enough, is that you follow this inverted potential. Over here, it doesn't, right? So because you have a different one composition, another composition here. On the surface, it's just going to have two ends. Okay, any other question? Okay. So, approach to coarse graining, we talked about. Okay, so I'm just going to kind of, not quite end, but I'm going to talk about transport in electrode. It's one thing that we did in terms of coarse graining. So in general, in the electrode, we don't have this kind of nice single layer, right, with a single material. We actually have multi-phase or polycrystalline material, multi-grain, and may even have like different materials in there, right, or pore. So all that needs to be taken into account when you try to define how well the material is going to overall transport lithium or electrons, etc. So then you can see this in the experimental micrographs. Most battery materials are like agglomerate of small particles, so you might look like this. Solid electrolyte is usually polycrystalline, so you can have like leakage through the grain boundaries and can have lithium. Oops. It was in solid oxide fuel cell. They sintered, so it's a polycrystalline. So it's very much interested in many different material systems and applications such as fuel cell, batteries, even corrosion, right? Because the polycrystalline nature of the material itself can affect the corrosion behavior. We have two things, two main things. One is develop accurate prediction with the direct simulation, and then develop accurate mean field description. So specifically for this particular problem, we can use the smooth boundary method that I talked about last time, and that include the effect of the microstructure on the transport. And then at the mean field, we looked at the different mean field approaches and compared the results and when certain approximations or certain descriptions are better, and eventually try to improve upon it. So, okay, so that's that. So in terms of grain boundary diffusion, so we looked at the grain boundary diffusion because it had this sharp interface model and other types of models. So you can describe the grain boundary diffusion when the grain boundary is parallel to the diffusion direction. There's a just sharp interface model to actually do the calculation, do the, well, it's a model. And it becomes like 1D problem. So, and then you have 2D and 3D. It gets a bit more complicated, and we have to use numerical method to simulate that. And so for that, as I mentioned, we use the smooth boundary method. You can look up the formulation, but basically it includes the enhancement or the hindrance of diffusion using this gradient of order parameter of different grains. So your one grain has 1 in that part grain and 0 everywhere else. Another order parameter would be 1 in specific grain and 0 outside, etc. So if you cut across this here, the profile of order parameter looks like this for 1 grain 4, or the order parameter 4, 5 looks like this, etc. And then you have this smooth in transition region that allows us to take this gradient of the order parameter, and then basically it allows us to be able, to mark those regions. And I'm not going to go over the derivation, but you can show that this SVM term is what we need in order to account for the hindered grain boundary diffusion. And we were able to show that when properly parameterizing these quantities, that goes into this kappa degree of hindrance that goes into the equation, it actually matches the sharp interface results. And the test microstructures are created by Dream 3D. And so you have a whole bunch of different microstructures. One is and a different number of grains, different amount of grain boundaries, grain boundary volume fraction, anisotropy, kind of one directional anisotropy, or this is like what is it, columnar grains. This is platelet grains. So these actually kind of encompasses different type of microstructures, kind of extreme of it, of 3 areas: isotropic, columnar, and platelet. So now we want some. So with this, we actually evaluated what the effective transport properties of the system is, and then now we want to compare with a coarse grain model, right? And the pre-existing coarse grain models are these. So the Maxwell Garnett had this kind of This is actually that's how we calculate it. We just calculate. We just calculate the flux. You just calculate. We set the boundary condition. Constant concentration one side, another concentration on the other side, and then just calculate the effective diffusivity through that system after calculating the average flux. Then, so the one major approximation that's been developed is by Hart, and that is like a parallel to the diffusion direction. So this is just grain boundary is flat and going this way, and then you have the diffusion going this way. Another one is the Maxwell-Garnett, which is kind of, you assume everything is spherical, and you get this expression. Epsilon here is the volume fraction of the grain boundary, and dB is bulk diffusivity. dG is the grain boundary diffusivity, same here. And then this is basically root of mixture, right? So it's very simple. And that just depends on how much of the grain boundary you got. Here, it's more complex because you have some tortuosity in the system. So here's the result. And what's calculated is this blue ones. So you can see that, and this is the diffusion direction, like this. So these are isotropic. This is both columnar, but this is along the elongation. The flux is along the elongation. This is perpendicular. So that's the difference. And then you see huge difference in what you get as an effective diffusivity. There's going to be a lot more tortuosity associated with going this way because you have to go up and down and up and down. This one is, the plates are going like this. And again, you have to go around those plates in order to get from one end to the other end. Whereas this one is like plates are going this way, so it's kind of like mostly straight shot. So, but then there's not as much of those. So you get high, but not as high as this one. And then these two are similar because there's a enhanced tortuosity. So another thing we did, okay, one thing I should say is that, okay, Hart's model, right, the root of mixture does pretty well, which is this one, light gray. It matches pretty well, right? For isotropic structures, Maxwell-Garnett does pretty well. Look, this is pretty good match, right? Maybe like within 10%, right? This, but the Hart's always overestimate. The Maxwell-Garnett is not as good here when you have something like this, but it's within the same order, or more error but not terrible, right? And then this is not great, right? It's getting factor of almost 2. The worst one was this one. Neither the Hart's or Maxwell-Garnett would predict it as well, predict the direct calculation. It's somewhere in between. It's almost like average. So we said, is there any way to improve on the description? So, and this is something, mathematicians might be interested in actually doing this properly. This, like all the things we did was pretty much intuitive way of thinking about this. So we thought about, okay, in order to transport material from here to here, what's important is having the interface oriented in parallel, right? So we came up with a projection of those areas that contributes to the transport in specific direction. So that's F act. So it's a projection. And then we adjust this volume fraction with this quantity that you projected. And then you use the projection, we use that to calculate the projection-based effective diffusivity. So when we did that, okay, well, there's a little bit more detail here. But when we did that, we actually did pretty good. So the new projection method is this blue. Yes, it's the projection method blue. And this is what was directly calculated. Matches, 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 and matches. So this is a nice kind of like a correction to the what's been around in terms of coarse-grained model for transport. And we were in process of trying to do this in a tensor form, which is still ongoing work. So those of you who are interested in working with us on this, I'll be happy to discuss. So that's where we are on this. So, so quick review. Basically, I just talked about transport and how I talked about grain boundary transport and the grain boundary assisted or hindered transport because it's easier to actually model compared to like having other bulk phases. So that's what I focused about, and I talked about projection method. Any questions before I wrap up? Okay, so my final thought. So I talked a lot about electrochemical dynamics in batteries. There's those equations, those resulting from mass conservation, those resulting from charge conservation, and the coupling at the interface with the reaction, electrochemistry. But the application of what I talked about can be beyond any electrochemical system. In fact, we work on corrosion, and you see the same set of equations. In this case, the difference is the metal surface can move, and we use a phase field model to account for the interface motion. Intercalation material is nice because the whole structure stays where they are, but you still have something like Butler-Boltzmann-like equation up there. You still have ionic transport, right, in the liquid. And then you still have an electrostatic potential, and then the coupling in this, right? So it's very, very, there are many applications for this. And again, I want to come back to this picture. The whole challenge is to not necessarily modeling those systems, but parameterizing properly. I think that's really, really important. And advances in multi-scale bridging is, I think, really, really key. So I hope that this IPAM is going to be a great venue to make advances in this area. Okay, so I just put the summary here, and I take any questions you may still have.